Good morning. This is Energy Physics here, and I'm going to start recording the very first of a lecture series in quantum physics and gravity. I've been, over the last 17 years or so, pursuing this as a hobby while I work as a real job doing software development, engineering. I'm an aerospace engineer by background. I worked on the space shuttle long time ago, former military combat pilot, and I've always had this interest in physics, really deep interest in understanding how things actually work. So over the last 17 years or so, and then publishing around 2012, I published a series of books and documents, primarily manuscripts that were evolving as the theories that I was developing evolved. And wasn't trying to do anything other than understand the truth based on current knowledge and environment that we have. So I'm going to do a series of these lectures and explain why I think we're on the edge of a new discovery of exactly what quantum gravity is and how it interacts with photon quantum and the rest of the world. The best way to do that, I figured, is to create a series of slides from the books that I first published in 2012. Most recently, a couple of papers I put out, about 8 of them, that were rejected because they're too speculative, obviously. Accepting this type of a theory would pretty much eliminate 80% of all the science and papers that are based on general relativity theories. It's not that general relativity is wrong, it's just an approximation, and it doesn't include quantum concepts or Planck scale physics. So the theories I've developed do include that, and you can answer a lot of questions with it that can't be answered by general relativity concepts or by current quantum field theory Lagrangians. So the big problem is the sensors that we have are not sensitive enough, detailed enough to measure extremely small particle physics. So most of the theory I've had, I've shared with some particle theorists and experimentalists, and they all seem to agree that this is the right approach. The theoretical physicists are very hesitant to accept this concept because it's a particle-only theory. There's no waves involved in this type of theory. It's a pure particle interaction. And it's based on the concept that the very first particles that formed out of the Big Bang were the gravity quantum, which I call a mass quantum. It's the smallest possible fermion with mass. And that began to freeze out first. Then came the photon quantum, froze out before the baryon and fermions were able to. And these are basically antiparticle pairs that are just too hot. The temperatures are and energy levels are too hot for them to actually form solid particles. So they just keep interacting as particle-antiparticle pairs until the universe got cool enough for them to combine and form the basic particles of our standard model. And this theory implies that at the very smallest scale, finite size in physics, the very smallest particles are the mass quantum, which has an incredibly small mass of about 10 to the minus 57 kilograms, which is completely unmeasurable by modern sensors. And the photon quantum, which has an incredibly small amount of mass also, contrary to Einstein's statements that it has zero mass or rest mass. And the reason for this is that in physics, everything is finite. You cannot have infinities. You cannot have zeros because that's nothing. So for any particle to be in existence, it has to have some very tiny amount of mass. We just can't measure it right now. And so this is the theory based on these two particles, the photon quantum and the mass quantum, interacting in ways to create all the other particles of the standard model, which are only 4 in their natural state. That's the proton, the neutron, the electron, and the neutrino. And these are basically, from this theory, composite structures which even form the small quarks that form the fermions, that are the particles with mass, and the bosons, which are the particles like photon quantum, gluons, and W plus, W minus, Z neutral, that form the other half. So this theory again implies that all of these particles are composite large numbers of Lagrangian energy summations that are supersummed mathematically based on their energy levels. And those energy levels in this theory are based on a concept known as a Lagrangian, and that Lagrangian is coming from Planck's original derivations. So both the mass quantum and the photon quantum have the same mathematical form. It's just they have different numerical values because the particle sizes are different and the masses are slightly different, quite a bit probably. But the interesting thing about this theory is you simply have to supersum all of the energy levels to come up to modern quantum theory estimates of mass and to equate to modern gravity theory based on general relativity. You can create the same numbers using a supersummation of energy Lagrangians of energy representations of the photon quantum interacting with mass quantum. And these are four states. Again, in modern physics, we don't recognize these states, but there are two bound states and two free states for each of these particles. The photon quantum has a free state that we recognize always travels at the velocity of c, and it never slows down. It just takes a longer time to travel from one event, a collision event, with another. And that collision event is an interaction with the mass quantum in its free state. And this mass quantum interacting with the photon creates gravity, a gravity collision type of a vector that the more you screen with larger masses, the less these free state mass quantum get through these larger masses, which causes an imbalance between the direction impacting the photon quantum from all the directions in the universe at an instant in time. And that slight imbalance creates the acceleration of gravity. And so that interaction event alone is a small delta in velocity that's balanced and kind of zigzags back and forth until it either moves toward the gravitational source of screening, because there's too many particles preventing the mass quantum free state particles from getting through, and those that don't get through are absorbed, and those are the bound state mass quantum that eventually form composites of quarks and fermions and the other mass particles of the Standard Model. The photon does the same thing. It interacts in all directions. You can get a balanced photon force when the photons are homogeneous from all directions and they impact an object of mass, which say an electron in free state. And the free state photons can actually create acceleration just like free state quantum creating acceleration. It's the same formula. And the bound state photons we don't talk about in modern physics, but those are the ones that are actually captured and trapped inside of the electrons that it interacts with, or the protons that it interacts with. And so we have this concept of force, the nuclear forces and the electromagnetic forces. And the electromagnetic force is basically the photon quantum going back and forth, it's called a boson, between the electron and the proton, and that forms what we call the electromagnetic force. But those protons are bound temporarily inside of the proton and inside the electron. While they're captured, they're not measurable. So basically we need to at some point understand that the photon quantum will change its state as it gets captured. It's an emission, transmission, and re-emission process, an absorption or emission process. And the photon quantum and the mass quantum have exactly the same behaviors in terms of emissions and absorptions. It's just the mass quantum travels through objects faster than the photon quantum because it's much, much smaller. It's on the order of 10 to the minus 75 meters or so. Minus 75 is incredibly small. You can't even measure that. So these are estimates that have come up with measuring the size of Planck stars versus neutron stars versus solar stars versus Earth-like objects, and trying to get an estimate on the density of how long it would take a mass quantum to get through or a photon quantum to actually get through. And it's thousands of years for highly dense objects. All right, without boring you too much with this initial introduction, I'm going to go to the slideshow. We'll sort of readdress this in a more logical fashion so you can grasp what I've been trying to say. Just remember that this is theoretical physics. It's not accepted by the common mainstream, but it's based on this very simple concept that all objects in the universe have to have finite size. You can't have any zeros, you can't have any infinities. All of our mathematics has zeros and infinities in general relativity and in quantum field theory. So we can't use those to do anything other than predict approximations of what's going on in reality down at the Planck scale. Planck scale is finite events between finite sized particles with finite velocities, and most importantly, finite energy levels, quantized energy levels, that are interestingly enough represented by an angular spin velocity that is a quantized value. It only has one value for each energy state. And that angular spin velocity is the energy, or basically the color of light as we see it, always traveling at the velocity of c. The velocity of c is, a constant in space. So none of these concepts violate any of the measurements in modern physics. We're just trying to look at it from a different perspective with a different understanding that waves are fooling us. Waves are composites of streamed particles, and when you stream them and then measure them over time, over human time, they look like waves. But the reality is they're solid particles impacting solid bodies like electrons, and they're sending signals that are based on other photons traveling back and forth and creating what we call an electric field and a magnetic field. The field itself is the photon traveling through space at the speed of light between these different events. So we'll go into these concepts in these slides later. That's about all I can think of to give you an overview. I'm recording in OBS Studio right now. I've tried to get the best quality I can out of this presentation so that we can, you won't be bored while you're watching this. So I have a set of slides here for gravity and general relativity, quantum gravity concepts. I did these slides in 2019 as a summary of my books that are out there. There's 5 books on quantum physics. And we'll just go into the slideshow version of this and start with the original beginning slide. So here's my concept. You have to start from the beginning somehow, and you have to ask yourself, what's reality? What does that mean to have something be real? And you have to separate something that's real from something that's not real, or false, or fantasy. And physics is full of fantasies. We've got wormhole fantasies, we've got time travel fantasies, we've got infinities in these wormholes, we have black holes that have these infinities down in the center, and even Stephen Hawking is starting to come around and say, no, the black hole really isn't an empty, infinite well that leads to a wormhole, that's somewhere down in there below the event horizon, which is just an event where gravity captures photons and won't let them out. There's a radius where that gravity is intense enough to keep the photons and every other particle of the Standard Model from coming out of a black hole. But somewhere deep down inside that, there's a solid core of all of these particles in existence that have been captured, and they're in incredibly hot temperatures. Not as hot as the beginning of the Big Bang, but they're really hot, almost plasma-like, and very likely particle-antiparticle pairs. Okay. So black holes is the result of gravity phenomenon, and you have to go ask yourself the question, how did all of that start? How did you get the very first mass quantum? How did we get the very first photon quantum? That's a huge intellectual concept for human beings to try to grasp. So my best representation of that is staring at this screen. What is reality? Well, if you don't have anything before it all started, it's just blank. It's all black. Let's say it's all black. There's nothing there. At least nothing that we can measure. That's probably the key aspect. It doesn't look like there's anything there. There's nothing interacting. And because there's nothing interacting, there's no motion, there's no visual evidence of something there. And if there's no interaction, then there's the appearance that it's empty. So we could say that when the universe started, there could be something there that is homogeneous, but it's not yet capable of interacting with anything. And it's not this vacuum state that everyone talks about, creating something out of nothing. It's something that basically had to start from the beginning as a homogeneous thing that doesn't have the capability to interact with anything and doesn't have the capability to create any motion or any physics. And we have to go beyond that and say, okay, well, what sparked the very first event in a Big Bang? And there's two ways to think of that. Something came into existence. Bang, right there. What was that? Well, it had to be the very first smallest possible particle in the known universe. This I'm calling the mass quantum. Measurements right now I have are 10 to the minus 57 kilograms at the Planck scale and below, and a size of about 10 to the minus 75 meters, which is incredibly smaller than the photon and the proton and the neutron and the electron and the neutrino of the particles that were formed out of the Big Bang. So this is pre-Big Bang stuff. Some particle comes into existence and starts a phenomenon of reality where this particle has a capability to exist and pop in and out of this state of non-measurement and into something that we can measure if our sensors are capable of going down to that scale. Right now they're not. They can't measure this little thing, but it's out there. There's hundreds of billions of millions of those things in every star in every galaxy that are interacting with every other piece of particle, free state quantum like itself, and they're creating gravity through a screening phenomenon where they clump together and they're so dense that nothing gets through, other particles get absorbed, and that creates an imbalance whenever a particle comes by that or near that or flies by it, and the particles on one side are hitting it more than the particles going through the stuff that's dense. That's called screening, and that creates a change in velocity vector and acceleration, and it looks like gravity. Gravity forces tugging toward the center of any mass. So the next step is, all right, it goes away. Somehow there's an event, an existence theory that I call it, where particles form, come into existence, and then they can pop back out of existence. And to me, that's not going back into nothing. It's going back into a state that you can't measure. Okay? It's not fantasy, and the problem is with things that are not measurable, they can be real, but just not measurable. But the problem is you can't tell the difference between those things and things that are fictional or fantasies. They're exactly the same. You can't prove them with any evidence or any type of experiment, any kind of truth, because truth requires measurement and requires existence, and you got to be able to measure that consistently over time. That's where you get experimental evidence of the truth. But when you can't measure it, there's no difference between that and pure fantasy. And that's why physics is in a terrible shape right now, because everybody is fantasizing about wormholes and physics realities of black holes, when in reality they're Planck stars. Big, massive objects that have so much gravity that they suck in every known particle of the universe of the Standard Model. And this is the little guy that's causing the huge gravitational forces down inside that Planck star. And it exists. You can't compress it past a certain point. There's a finite size. And at some point, if you get enough of them together, they blow up and they rebound. So there's a theory with that associated with the compression of how far does it go before these particles rebound and expand out and blow everything up. Okay, and they combine with photons and photon quantum in this process to do that. So this is the mass quantum when it was first created at the beginning of the Big Bang universe. I don't know the mechanism of how, but it came into and out of existence. Just like that. And bang, we got two of them. Now we got the first concept of potential motion, because we have two particles now that can interact. And without interaction, you can't have motion. You can't have evidence of inertia. So this is the condition for observing the physics of inertia between two particles interacting with each other. And these, okay, I gotta get my battery going here. How did that happen? 1 second. Wife unplugged it this morning. All right, now we got power. I'm sorry about that. So back to this reality concept. We've got two particles. Now we have evidence of inertia, evidence of motion when they interact. I call this interaction a CAE theory: collision, absorption, and emission. These two particles don't know about each other and don't interact until they get within some interaction radius, and they're able to deflect one another's velocities and change one another's accelerations. This is called momentum, and this is called inertia. And it's the inertia of gravity when it's a mass quantum that's interacting with another mass quantum that are in free states, and it's an interaction of forces for photon quantum when it's two photon quantum interacting in free states that cause each other to change in their deflections. And the same phenomenon happens when a free state photon interacts with a free state mass quantum, and that changes the velocity vectors of both of them and changes their inertia, and that's also gravity and photon inertia combined. So we have an equation that can represent these energy levels, and that equation is the same equation that Max Planck came up with, where the energy of one particle and the energy of the other particle combine together to have a total energy called an energy Lagrangian. And that energy Lagrangian for the Planck scale constant is the summation of energies are equal to, and this is all the particles that interact, the summation of the energies, Lagrangian energies of all the particles interacting, is the Planck constant h, or h dot, times the velocity of the particle. Now, the velocity that's in that equation is really not the linear velocity c, it's the angular spin velocity of that particle. And I call that an angular spin velocity because it's quantized, it has a single finite value, and each time it's emitted from an electron, it can have a different angular spin velocity. And so to have physics with the frequency, energy equals h dot nu, which is the angular spin velocity, times the Planck's constant, is the smallest possible energy state for this particle. You don't need to have wave theory to have that. You can have frequency, which is an angular spin velocity, but you don't have to have waves. You don't have to have a wavelength, because you can represent a spinning particle, and if you turn it on its side and put a dot on that, and as it rotates, it forms a waveform as you watch it travel at the speed of light spinning. It looks like a wave if you put a dot on it, but it's not really a wave. It's just a particle that's spinning around its center of mass, or center of the solid body that it is. It may not be a solid body, but it's probably a solid, finite, fixed-sized, quantized body. So that total energy summation, if it's a photon quantum, is E equal h bar nu, which is the angular spin velocity, a new way of looking at it, plus the gravity particle, which is g dot, just like h dot, g dot times omega, which is the angular spin velocity of the mass quantum particle, much, much smaller. But if you sum up all those energy levels, you can get the same numbers of any collision and any action between any photon and any fermion or any boson or any type of particle in the standard model. You can get the same energy calculations. All you need to know is the number of these particles that are interacting. And that's the basis of this theory. It's basically Planck's energy concepts, quantized energy concepts, supersummed to equal the modern values of the masses of objects in our universe, what we measure on a mass scale, and the energies that we register coming out of our particle accelerators. They're all supersummed into the total energies and total amounts of every single particle interacting with every other particle to get the masses that we're measuring in the accelerators. And that includes the Higgs particle, because it's a composite of these two particles interacting also. All the standard model particles, the neutrons, the neutrinos, the protons, the electrons, They're all composed of these two particles in both bound states and free states interacting. This is the basis of Planck scale physics as a description of how the universe most likely really works without our mathematics screwing it up and predicting infinities and zeros and weird phenomena that don't exist like wormholes and time travel and all that other junk where humans can't possibly survive. You're never going to survive going down a black hole. And it's ridiculous the number of people that believe that we can go down a black hole and come out the other end of that as human beings. You're going to get roasted before you even get close enough. The gamma radiation alone is going to just cause your entire body to just disassociate. So get real. This stuff's really hot temperature. And when it's by itself, it's really cold temperature. Some of the coldest temperatures in the universe are a single rotating mass quantum and a single rotating photon quantum at the cosmic background radiation level because it's never interacted with anything. It's been spinning and slowing down its entire travel distance of 13.5 billion years to go from way back where it existed on the edge of its first formation to where it actually comes to us in local space and gets measured right now in one of our detectors. So the universe is a composite picture in time of all of these particles as they come at our present space, coming from different time zones and different distances away. So the real picture we see the night sky is not really the picture that it is right now. It's a composite of all these different time layers. So it's a false image. It really isn't. It's a virtual image of composite particle evidence. So we need to think about that. That's general relativity because it takes time to travel. All these particles can only travel at the speed of light. Maybe the photon quantum can travel a little less, but I doubt it. And maybe back then it was traveling a little faster. We don't know because we can't measure anything but today. And the mass quantum may travel slightly faster because it can go through planets a little faster than photon quantum, and that's proven by the LIGO's experiments where the neutron stars exploded and put out a stream of these tiny little mass quantum particles that slammed into that 2 mile long or mile long piece of steel rod and caused it to oscillate and change the values of the two interferometers on the ends to where we have something measurable. And that signal is not a bunch of waves. It's stochastic. It's a streaming, very choppy signal that is perfectly aligned with the existence of a particle stream, not a wave coming at us. It's not a gravity wave. So let's get the right concepts physicists out there. Stop using wave theory. Let go of Christian Huygens and that age-old debate between Newton and Huygens and everybody else who's ever debated, particles versus waves. Everything's a particle interacting, and waves are only group phenomenon that look like waves over composite human time. But it's still all particles interacting. And I call that theory the CAE theory, the collision, absorption, emission theory, with the energy Lagrangian summing to the summation of all the energies is equal to h dot nu plus g dot omega. All combinations of the gravity quantum energies in summation with the photon quantum energies create all motion and all evidence of inertia, which is both gravity and photon force fields. And I don't want to use the word field because of its own implied problems with it's a 0 point at every point in space and it has no values until you put some amplitude on it. That's just another set of mathematics that's misleading our understanding of the true nature of the universe. So this is I'm sorry to have to make such a long lecture, but we've got to understand how to formulate this concept from the beginning. And let's say we got an antiparticle-particle pair, the two little red dots there, and they're going to interact. And from this, we define space. Everything outside of that little particle before it came into existence, we're going to call exospace. And everything inside of the radius of that finite-sized particle, whether it's a mass quantum or a photon quantum, we're going to call that finite space. So the concept is there's some radius, and it can fluctuate based on compression or other factors of how many other particles are next to it, but it has a free state radius that's probably fixed for each of the particles. The photon quantum probably has a fixed finite space, and the mass quantum probably has a fixed finite space. And those two spaces, in terms of size, are probably not the same. I estimate the mass quantum is, again, around 10 to the minus 75 meters in size. That's really, really small. Inside and outside, you've got space and antispace concepts. And antispace would be the antiparticle that's created when you have two particles come together and they change state. And the state change is they go from being mass quantum to photon quantum. And they go from photon quantum to being mass quantum, because that state particle-antiparticle interaction translates the masses to energy levels at those very high energies. They can't form solid particles. So there's got to be some way that they can interact, and a difference between finite space and antispace concepts. So I'm really making this claim that reality, existence of a particle, is what we call anti-space. It's something other than empty space. The problem with reality is that it's hard to measure it, and if you do measure it, you get composites. We do know for evidence that composite particles in time create special relativity illusions that we have to account for. But these composite illusions are quite often ignored, but they always exist. And the only the particle itself knows local space. Human beings are going to measure relative space, relative motion, relative inertia, relative accelerations because of the time distance that it takes the particle to go from its local space collision to reach our point in space where we measure it. That delay is called special relativity. That's all it is. And the particles bounce from one particle to another, and they take longer if there's more particle interactions between where it originated and where it finally ends up where we can measure it. That's a delay in special relativity. And so it looks like the further away it is, the slower it goes, but it doesn't. It doesn't travel any slower through space, going from particle to particle. Always travels in free space at the speed of light. But it slows down by the number of particles that it has to interact with and by having to travel a longer distance. That longer distance is the special relativity. It's also known as an index of refraction, or an index where it looks like its frequency is changing and its wavelength is changing, but in reality, that's just a phenomenon of traveling a longer distance because there's more particles between the point where it originated and the point where we're able to measure it. So the other concept is get rid of the singularities. We don't need to have waves to explain anything because that implies an ether. We just need empty space and finite particles with no singularities, no infinities, no time travel, no multiple worlds, no entangled interference, no entangled in quantum entanglement. All we need is a change of a single quantized photon, quantum, and mass quantum state each time it interacts with another quantum particle. It changes direction, it has a discrete quantized energy level, and it changes polarity, which is the particle-antiparticle concept. The spin is in an opposite direction. Real angular spin velocity is in one direction or the other, and depending on what direction it's spinning determines the chilarity, I think that's what it's called, of whether or not it has a left spin or a right spin or only left spins in the case of, say, neutrinos. So these concepts are not difficult to speculate and theorize, but very difficult to provide evidence of except in particle accelerators. And right now we're in a state where the mass quantum is so small and so light that we can't measure it with our modern sensors, and that's the problem. That mass quantum is responsible for dark energy interactions, which is the expansion of the universe, and it's responsible for dark matter interactions with other photon quantum and other bound state fermions that cause the gravity and the collapse of all the mass quantum and photon quantum into galaxies and stars and Planck stars and neutron stars. And it's just those two particles interacting to go from free states and interact to bound states. And they're captured, some of them at the beginning of time, and have never been released. There's photon quantum bound inside of every proton. And there's mass quantum bound inside every proton. And if you manage to release those by putting that proton into high energy accelerator and slamming it into another proton, you get enormous conversions of the bound state photon quantum and the bound state mass quantum being released into massive amounts of energy of free state photon quantum that have angular spin velocity energies that are quantized. And you also have the mass quantum being released, but it's missing mass because you can't measure it. That's why we're pursuing and looking at the Higgs boson. It's our attempt to explain, how do we account for this missing mass? Well, the Higgs boson itself is really a composite of quarks and a bunch of other particles. So at its smallest level, even the quarks are composed of composites of the smallest possible mass in the universe, which I'm calling the mass quantum. And it binds and it gets free. And it binds with photons and it gets free. And it interacts with photons and it changes inertias and it changes momentums. LIGO is the first evidence of that mass quantum. Look at that signal. That's not a wave. That's not a wave function. That's nothing to do with wave theories. That's a composite picture of thousands of little tiny mass quantum slamming into that steel rod and causing it to vibrate because it's pushing the electrons and pushing the protons back and forth every time a particle interacts with it. And more of them are pushing the particles in one direction than there are coming through the Earth and pushing it with less force and less acceleration and less momentum because it's being screened by all the fermion mass that composes the Earth. That's gravity. That's what's holding me in my seat right now. All the mass quantum that are slamming into all the protons and neutrons and neutrinos and electrons in my body are pushing me down toward the center of the Earth. Every time they hit, they change a small, tiny bit of my momentum in the direction of the center of the Earth. Because there's more of them coming from the direction of outside space than there are getting through the Earth, underneath me, where my chair is. Why is that? Because they're being absorbed. Those tiny little mass quantum don't all get through. They'll take thousands of years, maybe 100, maybe 10 days, I don't know, to get through the Earth and slam into my body from the other direction. But there's a differential in the number of them that impact from the bottom and the number of them that impact from the top. All of the photons interacting with my body and all of the protons being hit by mass quantum and by photon quantum, all those create energy levels and accelerations in one direction because of an imbalance in the number of particles that are colliding and interacting in a specific direction. That's gravity. That's force inertia caused by photons. You know, cars move because photons push things. They push the gas molecules in your car engine. That's the phenomenon of photon inertia and momentum. But gravity does the same thing, and it's almost indistinguishable except for a couple of phenomena, like Cherenkov radiation. Cherenkov radiation emits photons because there's photons that are doing the interaction and the pushing. But in a black hole, or better, Planck star is what better term, they're pushing photon quantums that are not doing the pushing. It's the mass quantum that are doing the pushing, and they're what get emitted as the gravity works on the Planck star, and it emits mass quantum instead of photon quantum. But you can't see them and you can't measure them. That's why in Cherenkov radiation you get photon emission and you don't get photon emission for Cherenkov radiation in a gravity well. And that's how you tell the difference. It's two different particles causing that phenomenon. One is emitted photons as they get close to the speed of light. The other is emitted mass quantum as they get close to the speed of light. Same phenomenon, just different particles, explaining the difference between Cherenkov radiation, which has been an enigma for many years. Same thing happens with the Casimir effect between two large plates. Okay, and the inside of the plate, there's not enough source quantum, photon quantum or mass quantum, to push the insides of the plates outward. The sources are just less. And there's more of them coming from the rest of the universe outside the plates. And so as they slam into every single quark, every single electron, every single neutrino, every single proton, every neutron that's in the molecules of those two plates that are so close together, they push them together. That's the Casimir effect. And it's because of the existence of free state photon quantum and free state mass quantum slamming into these sizes in different numbers with an imbalance on one side that's less numbers of particles hitting all the molecules from one direction than from the other. And that imbalance creates motion and it creates gravity. And you can see it in this LIGO detection. Those are mass quantum coming from those two neutron stars that are colliding. And guess what? They're coming in at different energy levels, different angular spin velocities based on the type of state of the electron or the proton was in and how much energy was in that. These are very high energy mass quantum. If they came from background radiation, they're coming in at absolute zero. They're really cold. These mass quantum are hot. They've got really high energy levels, and that's why we can observe them. But the mass quantum coming from cosmic background energies, they're so cold they're near absolute zero, and their angular spin velocities are almost zero. Not zero, but really close to it. So mass quantum is cold when it never interacts with anything on its travel through the universe, or just a couple of particles, and it gets hot when it's interacting with exploding neutron stars or two Planck stars that are running into each other. And that's why we're seeing a gravity signal, which is a pulse of gravity-based mass quantum, not gravity waves. Gee, Einstein's relativity, nobody's willing to abandon it. It's an approximation, and it works good for what it works for. But it doesn't explain the quantum phenomenon, and it doesn't explain single particle interaction at the Planck scale. But LIGO is the very first evidence that the mass quantum arrived first 1.7 seconds before the photon quantum. Something arrived first because it went through all the stars and all the planets quicker than the photon quantum, because they had to go around and be bent by the gravity interactions of these other mass sources. That's why there's a difference. Gravity, mass quantum can travel through planets faster than photon quantum. And the evidence of that is here in the LIGO detection gravity event. We're going to blow through a lot of these charts. It's all the same. Everybody tries to convert it into waves now, and they try to reduce the waveforms. But the tiny little dots, okay, those are composite single collisions, and there's thousands of them, and when you put them all together, it forms a composite picture that looks like a wave signal, but it's really jagged, and it's really blurry, and it's just like interferometry and how photons go around the edges of doors and collide with the electrons, and they go off in different directions, and they form these really cool little, patterns of light and dark, light and dark, light and dark. It's just because in the dark spaces, there's no particles that hit there, and in the light spaces, all the particles concentrate and bounce back, and we can see them with our eyes because they're a high enough energy in the visible light spectrum for our eyeball to detect it. This is just the directions of where these mass quantum are coming from as a composite picture in the universe. So let's define mass. Okay, we got some numbers. Photons, gamma, symbol, somewhere around 3 times 10 to the minus 27 in terms of its mass. The energy level is 1.6 times 10 to the minus 19 joules. That's an electron volt, if it has that. The charge on the photon is its direction of spin. It can be polarized, spin one way, or polarized, spin the other way. That's the angular spin velocity that has a finite energy level. And if you see this equation that the sum of all the energies of the photons is h bar nu, or omega, plus or minus g dot omega, which is the mass quantum, and that can be equal to the summation of all the mass quantums times the velocity of light squared. In other words, energy equals mc squared can be converted to the summation of all the energy levels of all the mass quantum added up and all the photon quantum added up as they go back and forth between particle and antiparticle interactions, which would be called annihilation. But all they're doing is going from visible photon quantum to invisible mass quantum, depending on the direction of the interaction. If gravity squeezes them, you can get photons. If photons explode, you can get mass quantum releases. And that conversion happens when you convert the fermions in the particles of the Standard Model into pure photon quantum energy levels. And these energy levels were bound into these particles from the beginning of the universe. They're indestructible, except when you heat them up in particle accelerations and you get them hot enough to come apart in quark-quark interactions as you search for the Higgs particle. Simply put, everything interacts as a finite particle. Those particles we can say are actually anti-space, or the opposite of space. They all have a finite radius. They all have a finite angular spin velocity that's quantized, meaning it has only one value. And you can do the number of those angular spin velocities will equal the energy levels that we detect in a light spectrum, for example. And that's how you get red, blues, and greens and all that. It's just different angular spin velocities that are quantized. They can only exist at certain frequencies, and if they don't exist at other frequencies, it's just black. That's how you get the stellar lines. And I can pop out and show you what that looks like. What does a typical spectroscopic light shift look like, red shifting. We'll talk about that. But the formula is very easy and simple. It's just a summation of all the Lagrangian energies, and you can make them equal to the typical Lagrangians of the modern field equations, which I've done in my books. All of quantum field theory is a bunch of Lagrangians with basically Hermitian matrices and quantum statistics representing each of those energy, all the possible energy states. G dot has been approximated by calculations I've made on Planck stars and neutron stars and regular stars and Earth-like planets to be about 1.05 times 10 to the minus 77 joule second. H and H bar, which is the Planck constants we know about, those are already measurable. G dot is not. And look at the difference in terms of the scale, in terms of energy levels in just one particle. That's the smallest possible energy quantum in a single mass quantum. And someday we're going to be able to measure that, and this theory will be proven valid, and the world will begin to understand that everything's a particle, and nothing's infinite, and nothing's zero. There's no wormholes, and there's no time travel. And flying through space takes a long time because of special relativity, and we may never get very far as human beings because we're going to be torn apart at some point because our bodies just can't handle all these mass collisions that we have to go through to go very far. So there's a reality there. So, we've used the current quantum field theory for interactions between photon quantum and mass quantum, which is fermions. And those are represented on the left-hand side by these state vectors, this U1 times SU2 times SU3. This is the gluon nuclear forces. There's 3 color charges. And So that's all mathematically formulated pretty much with these Hermitian tensor fields, unitary or special unitary tensor fields. And again, they're energy Lagrangians that are summed together. So the theory that I'm using is not very much different than that. It's just not using matrix mathematics and statistical mathematics. It's just using finite, quantized, discrete mathematics. In other words, everything is a discrete summation. There is no continuous equations. Most of our equations look for continuity, and that's why they have infinities and zeros. This mathematics is just a finite mathematics that sums finite values over large numbers, and computers can do that. So we have no problem calculating the number of photon quantum that hit and create, the energy in a generator, or the energy in water, or the energy that impacts the Earth. That can be measured into numbers of photons that collide, and it can be measured in a number of mass quantum that collide with the planet and move the planet around the sun. That's all calculatable. It's just extremely large numbers. And then we go into, here's the gamma photon going between an electron and a quark. Its representation, and that in a neutrino electron interaction, this is a W plus or a W minus particle. There's also possibly a neutral current Z0, and that's again all the U1, SU2 unitary, special unitary matrices for SU3 Hermitian calculations of quantum statistics, which we don't need any of that. Except as an approximation. This super summation of Lagrangian numbers between mass quantum and photon quantum in 4 states is really all we need to calculate energy levels in every particle of the Standard Model and every interaction in a particle accelerator. And that's why the theory is so speculative, and that's why my papers haven't been accepted, because it would invalidate all this mathematics that everybody gets crazy over because it's so complex. And the formulations I have are very simple. It's a simple energy summations. It doesn't take anything other than a supercomputer to add them all up. And experimentalists do that anyway when they measure the energy levels coming out of particle accelerators. They're all finite, supersummed energies. So the experimentalists understand and agree with the equations I've developed. The theorists are scared to death of it and won't accept it. So, again, what's the smallest possible finite quantized particle? There's your mass quantum, the little red dots, and that's that imbalance. The little red dots on the bottom are coming up through the Earth, and they're hitting the photon quantum as it flies past the Earth from the sun. And because there's less of them interacting and colliding, and more of them interacting and colliding from deep space, this is dark matter. This is gravity. This is the small mass quantum is dark matter. And it causes photons to change their acceleration and change their velocity vectors and their momentum. And this is all the screening of the stuff coming through the Earth. There's just less of them. There's just as many on the other side impacting, but they don't get through. They get absorbed. And absorption is a phenomenon that we know well with photons. It's the same mathematics of photon mathematics that we accept. We just have to apply the same math in smaller quantities to mass quantum to get the same numbers and the same calculated values that we get in any modern accelerator experiment. It's not hard to conceptualize and do those calculations. So we go from Newtonian scale approximations to nuclear scale quantized approximations, and everything's a zigzag. Those are all collisions zigzagging through space. And the smaller we go, the longer the scale of it looks like between the Planck scale between events. And what does general relativity do? It tries to smooth all that out into a Riemann set of matrices. And that's why general relativity can't handle the individual particles, because it's operating at human size scales. And it works good for, calculating the mass of gravity interaction on a sun or a planet, but it can't do that for an individual nuclear particle, like the gravity interacting on a photon or gravity interacting on an electron. My theory will do that, but general relativity cannot because it's not based on that. And the interesting thing is that quantum field theory can calculate the same energy levels, but it can't calculate the gravity because it's left out. So both theories are insufficient explanations of the reality of the universe. And in the equations I've used, I've tried to make sure we include both phenomena, both the gravity particle and the photon particle behaviors interacting in these little zigzag type collision, absorption, emission events, always traveling at the speed of light between the events, being delayed by special relativity because it travels longer distances than it does if it's a smooth curve. It looks like a smooth curve on a Newtonian scale calculation. A little 1 over r squared fall off of gravity. So, provable that 1 over r squared is actually a bunch of zigzag little events between millions of mass quantum interacting with millions of photon quantum. So again, the theories are based on differences of view. The Higgs boson using the standard models. The universe scale of 14.375 billion years is using general relativity. So general relativity works good for large scale blank star approximations. The supersymmetry theories and other nuclear theories to estimate the standard model. Higgs boson existence all happen as a middle type of a calculation, which isn't compatible between general relativity and quantum field theories, or quantum electrodynamics and quantum chromodynamics, as they used to be called. They're now combined as energy Lagrangians with these wonderful Higgs approximations added in. But you go below that and you get to Planck scale collisions, and it has to be simple. Just simple quantized interactions, simple spin, angular spin velocities, simple momentum changes, and simple velocity changes, and simple accelerations all add up based on how many objects arrive at space at the same time, how many come from one direction, how many come from another, and if there's an imbalance in that number because of screening, because they've been absorbed by masses of boson, fermion type particles on their way, there'll be less of them, and you'll get gravity or photon inertia changes, pushing stuff, forcing stuff, and moving stuff in one direction. If the balance is there, everything will look like it's suspended in space at zero gravity. You're just going to float. That's what zero gravity is. All the forces and all the interactions are balanced in terms of the numbers of particles hitting from all directions. And this is why dark energy and dark matter have an imbalance. There's an imbalance in the number of particles streaming outward, and that causes acceleration on the outward side because there's nothing to oppose all the fermions that are spreading out in space after the Big Bang. There's nothing to push them back. So that's why everything's accelerating, is that all of the interaction is occurring from the center of when all of that occurred, and there's nothing to balance that on the outside. It's as if one big, huge universe screened all those particles out because they don't exist out there beyond the known universe. So it's rapidly expanding, and we'll probably keep on rapidly expanding. Whereas inside of the universe, there's enough homogeneous particle spread that it can still compress from all directions. It can still get screening bodies to clump together that grow and grow and grow, and as they clump together, they form planets and they form stars, and the stars create, they come into life because of the massive amount of particles that are interacting, hitting them from all directions, squeezing them down into tiny little volumes, and eventually they grow and grow and grow and become black holes, and then big threads of galaxies. Black holes are Planck stars at the center of every galaxy in a big thread of dark matter phenomenon at the universe scale, and we can see all that. But again, that's a halo of mass quantum particles causing those two phenomena based on the amount of particles that exist in a given location in space. And so gravity could have been stronger in the past than it is now because things have spread out. There's less of them and there's less density. So gravity could be continually get weaker and weaker and weaker in local space in current time than it was in universe space 13 billion light years away when it first started. That would be enormous energy levels and enormous numbers of these quantized particles being created. So I'm not going to go into the details of this chirality, helicity for relativistic waveforms and all that. This is all going back to identifying parity and existing acceleration. These Hilbert space state vectors being calculated, and particles or half integer spins and stuff like that. Those spins are mathematical matrix spin numbers, and they're just used to divide things up into symmetries. But they're not the angular spin velocities that I'm talking about, which is the reality of particles actually rotating, and as they interact with each other, they cause curvature if they're electrons in one direction. If they spin in the other, they cause a curvature of electrons interacting with photons in the other direction, which is called a positron. So you got an electron being a particle, and then you got an antiparticle, which is the positron, spinning in the other direction because the photon quantum and the mass quantum that are interacting to cause that are spinning in the opposite direction. And that's a real photon field and a real free state mass quantum field causing those directional changes in your accelerator, particle accelerator. It's a tiny contribution of gravity and a huge contribution of photon quantum that form what are called a field, but it's really the photon flying everywhere and hitting everything. That's what we try to define as a field, but it's not really a field. It's just a mathematical representation of real particles spread out, flying everywhere, interacting with collisions, absorption, and emissions, and causing momentum changes and acceleration changes based on the directions that they spin and the energy levels that they carry in terms of frequency of angular spin velocity. That's momentum changes. So there are a number of concepts I just try to throw in here. There's a Newtonian gravitational concept that is trying to imply a force at a distance. Newton didn't really say that, and he understood that there has to be some kind of a particle interaction between them. And the only guy that is his peer at the time that understood that was I can't remember the guy's name now. It's in my books, LaForge, whatever. Yeah, it's a shame. Two guys basically proposed these types of particle theories for gravity, and they were pretty much ignored, and then people debated particle versus wave ever since then. Special relativity at the Planck scale is really all about how long does it take a photon quantum to get from an electron to another electron when that electron is moving. And as soon as that photon comes out of its electron escape velocity, it always travels at the same velocity because the escape velocity is always the same. Now, why is that? Because the electron shell itself, the electron size, releases that photon always at the same velocity, c. So when there's two events happening out there, it takes a finite amount of time for a photon to travel to one event, which is an electron, and be absorbed and re-emitted, and then travel to another event at the speed of light and then be absorbed and emitted. And that delay in human time that we measure is special relativity. Only it's really happening at the Planck scale, not at the human scale. It's not elevators, it's not trains, it's not clocks like Einstein. His analogies are wrong because he's picked the wrong sizes. It's really special relativity of nuclear, photon, and quantum physics-sized particles. Special relativity of mass quantum interacting over long distances, special relativity of mass photon quantum interacting with masses over long distances. And those take time to get to detectors. By the time they bounce off the second interaction and get to the electron to be detected, there's a finite time that has to pass. And so we see into the past a composite image of that We cannot see what's happening right now because the detector can't measure what's happening right now. It always measures an event that takes time from the human perspective. But the particle itself, it knows real space. It knows local space. It knows non-relative space, which is the elusive concept that people have been debating. Is there a non-relative frame? Only the particles know what position they were in relative to space and relative to their velocity, constant speed of light. They're the only ones that detect that and actually cause that. Humans cannot detect that. We will always detect relative speeds and relative phenomena because we're too big, and the particles take time and delay time, even though because they travel at the speed of light, and they take time to get to us, carrying that information, which ends up being a composite picture, not a simultaneous picture of what happens back then or right now. Those are two different images. So our images are false. If we measure one event and then measure another event, they're delayed in time. They form a composite picture, which is not at the same instant in time. There is no simultaneity there, except between the two particles that interact and start the phenomenon to begin with, which is a photon quantum interaction with a mass quantum. And they can be interacting in free states or bound states. They still have the same ability to change inertia and change acceleration and momentum. So I'm not going to go into that, any more detail than that. This is all, again, trying to depict what's happening at the quantum scale. Antiquark baryogenesis happened at the beginning of the universe, and why is it delayed? And again, why is it a particle-antiparticle interaction that either can stay in a bound state or not stay in a bound state based on its overall energy and temperature. And these are just my attempts at trying to visualize those interactions. Now, I went through a review of the tensor operations necessary to understand general relativity. I don't want to create our lecture about this. Sometime I'll put out a lecture on how general relativity was defined in terms of tensor mathematics. But it's basically a bunch of vectors, and then those vectors have accelerations. And because those accelerations are second order, you got to have things called Riemann curvatures and Ricci tensors, and all these g's minus 1/2 g u v r equal 8 pi t, which is the tensor side versus the gravity side. Those are all matrices, and they have to involve matrix calculations that's statistical, and that gets messy when you start believing the mathematics is the reality. So it's again, the metric tensor, all that calculation is an approximation. Metric tensor is an identity tensor. It basically says everything is along a diagonal, and some beautiful mathematics, but it doesn't really help us get to the real physical reality of particles interacting with other particles. It predicts waves and predicts general relativity phenomena that's an approximation of the realities. It can't calculate stuff going on at the Planck scale or even the quantum scale. So it's a beautiful theory. We rely on it too much. Too many people are afraid of it. Changes to it will destroy their careers, so they won't accept this pure particle explanation of how all the particles in the standard model are created and how gravity is changed by particle collision and particle interaction and screening of absorbing these particles wherever there's a large mass collection of them all sticking together. So, you can go review this. I'm trying to go through it fairly slowly that you can absorb a little bit of it, but it's a fun math to work with, but it's very tedious, especially when you get to the understanding why there's a Christoffel symbol, and it's the mathematics of doing derivatives, on derivatives and vectors. So it's just it's the rules of math on how you do vector calculus. And then at the Planck scale, we talk about broken supersymmetry and broken gauge invariance. These are all attempts to explain the phenomenon, even using loop theory, superstring, supersymmetry. trying to come up with ways of getting rid of those infinities and getting rid of those zeros within the existing framework of the existing quantum field theory. And the problem is it doesn't include gravity, and so it's always going to be an approximation until the gravity phenomenon is accounted for. And if you go back and just understand that gravity is just another particle that's interacting with every other particle, and it changes momentum and it changes inertia, and you go with that supersumming finite values that are quantized finite spin angles to get quantized finite energy levels, supersum those called Lagrangians till you reach the same numbers and calculations that you get by calculating with superstring theory and general relativity theory and quantum field theory. It's just a different way of binning and bucketing the energy quanta. Oh, go back one. No. Let's go previous. I think we can test for this. The LIGO gravity detector is already doing it, but to test for the collision theory, I think we need binary star interactions, and we need to have supernova, and we need to have them interact with each other directly and locally, and then through this concept of which gets here first, just like it did with LIGO gravity, we can detect some type of finite energy level of mass quantum impacting our detector. So the detector has to be a universal, very large scale detector out in space, I think, to detect anything that's low energy, like near absolute zero, cosmic background, quantum, dark matter, and dark energy. That's going to be very, very cold, even colder than the 2 Kelvin cosmic background radiation of photon quantum that have been traveling for 13 billion years and haven't interacted with very many particles. Mass quantum been doing the same thing, and yet they can't regenerate inside of stars or Planck stars because most likely they are the cause of fusion and can't be created by fusion again. I think they're only going to be created by Big Bang type energy levels, and photon quantum doesn't need Big Bang type energy levels to be fused and created again at higher energy levels. So we'll see how this theory pans out in the future. You can look at another couple of papers and books I've written on beyond the standard model and general relativity, and I go into what is it, space and anti-space, and how do we get mass quantum, and what are their sizes, and how do we look at the collections and the specs, and how do we do the mathematics in discrete type mathematical modeling, and what does that look like, in terms of graphics and particles together, and trying to do different representations of how these particles collide and create bounded space and form composites of all the other known particles in the standard model, and interact, to create gravity because of the particles clumping together and a bunch of free state stuff and a bunch of bound state stuff, creating inertia and then interacting. So it's a fairly simple theory, but it's one where people just get skittish when they start thinking that, this is too simple, it's going to invalidate all of my theories and papers. And that's what happens when I submit my papers to the American Physics Society. The gatekeepers there go, this is too speculative, but they have no evidence and no proof that any of it's wrong. It just scares them because it invalidates all of their work, especially if they're gravity theorists that have relied entirely on general relativity in their assumptions. And that's what Stephen Hawking has done. Everybody's relied on general relativity being accurate enough, but it's never accurate enough to do quantum level calculations. Going in, it can't do any quantum calculating. Whereas this theory can. The CAE collision theory that I've formulated, collision, absorption, and emission phenomenon are identical between photon quantum and mass quantum, and we use the same mathematics, just different Planck constant values and gravity constant values. Someday I think you're going to find out that's the real physics. So I'm going to end this at this point. Escape back out. And call it the end of the lecture for the day. I hope you've enjoyed it. I hope it makes some sense to you. If you want to get more detail, look up my books. It's always under How to Succeed at Understanding Gravity, M. Hatcher, Amazon Publishing, How to Succeed at Understanding Quantum Field Theory, How to Succeed at Understanding Newtonian Theory, The other two books are How to Understand the Universe and How to Understand, gravity theory. You should enjoy those books if you want to understand science from a slightly different perspective. That's not wrong, easier to understand, and just too speculative for people to yet adopt it. But it certainly explains a lot of 8 different phenomena that are not explainable by either quantum field theory or general relativity. And this approach explains those interactions, and I've described those in the papers that I put into the last book I wrote. Submitted the papers, I think, back in 2017 or so, and there were 8 of them. And finally, when I realized they weren't going to be published, I incorporated them into the last big book where we talked about the LIGOS gravity experiment. So if you're interested in seeing the formulations of those again are evolving manuscripts, just head out to Amazon, and you'll find it under M. Hatcher, How to Succeed in Understanding Quantum Gravity, General Relativity, Quantum Field Theory, Newtonian Physics, all those. Take care.